The Riemann zeta function or Euler-Riemann zeta function, zeta, is a function of a complex variable S that analytically continues the sum of the infinite series which converges when the real part of S is greater than 1. More general representations of zeta for all S are given below. As a function of a real variable, Leonhard Euler first introduced and studied it in the first half of the 18th century without using complex analysis, which was not available at the time. Bernhard Riemann's 1859 article, on the number of primes less than a given magnitude, extended the Euler definition to a complex variable, proved its meromorphic continuation and functional equation, and established a relation between its zeros and the distribution of prime numbers. The values of the Riemann zeta function at even positive integers were computed by Euler. The first of them, zeta, provides a solution to the Basel problem. In 1979 Appert proved the irrationality of zeta. The values at negative integer points, also found by Euler, are rational numbers and play an important role in the theory of modular forms. Many generalizations of the Riemann zeta function, such as Dirichlet series, Dirichlet L functions and L functions, are known. Definition: the Riemann zeta function zeta is a function of a complex variable S equals sigma plus it. The following infinite series converges for all complex numbers S with real part greater than 1, and defines zeta in this case. It can also be defined by the integral where gamma is the gamma function. The Riemann zeta function is defined as the analytic continuation of the function defined for sigma greater than 1 by the sum of the preceding series. Leonhard Euler considered the above series in 1740 for positive integer values of S, and later Chebyshev extended the definition to real S greater than 1. The above series is a prototypical Dirichlet series that converges absolutely to an analytic function for S such that sigma greater than 1 and diverges for all other values of S. Riemann showed that the function defined by the series on the half-plane of convergence can be continued analytically to all complex values S1. For S equals 1 the series is the harmonic series which diverges to plus infinity, and thus the Riemann zeta function is a meromorphic function on the whole complex S-plane, which is holomorphic everywhere except for a simple pole at S equals 1 with residue 1. Specific values. For any positive even integer 2n, where b2n is a Bernoulli number. For negative integers, 1 has for n1, so in particular zeta vanishes at the negative even integers because bm equals 0 for all odd m other than 1. For odd positive integers, no such simple expression is known, although these values are thought to be related to the algebraic K-theory of the integers. See special values of L functions. Via analytic continuation, one can show that gives a way to assign a finite result to the divergent series 1 plus 2 plus 3 plus 4 plus, which can be useful in certain contexts such as string theory. This is employed in calculating of kinetic boundary layer problems of linear kinetic equations. If we approach from numbers larger than 1, then this is the harmonic series. But its Cauchy principal value exists, which is the Euler-Mastroianni constant. This is employed in calculating the critical temperature for a Bose-Einstein condensate in a box with periodic boundary conditions, and for spin wave physics in magnetic systems. The demonstration of this equality is known as the Basel problem. The reciprocal of this sum answers the question, what is the probability that two numbers selected at random are relatively prime? This is called Appert's constant. This appears when integrating Planck's law to derive the Stefan-Boltzmann law in physics. Euler product formula. The connection between the zeta function and prime numbers was discovered by Euler, who proved the identity where, by definition, the left-hand side is zeta and the infinite product on the right-hand side extends over all prime numbers p. Both sides of the Euler product formula converge for r greater than 1. The proof of Euler's identity uses only the formula for the geometric series and the fundamental theorem of arithmetic. Since the harmonic series, obtained when S equals 1, diverges, Euler's formula implies that there are infinitely many primes. The Euler product formula can be used to calculate the asymptotic probability that S randomly selected integers are setwise coprime. Intuitively, the probability that any single number is divisible by a prime, p, is 1, p. Hence the probability that S numbers are all divisible by this prime is 1, ps, and the probability that at least one of them is not is 1 minus 1, ps. Now, for distinct primes, these divisibility events are mutually independent because the candidate devises a coprime. Thus, the asymptotic probability that S numbers are coprime is given by a product over all primes. The functional equation. The Riemann zeta function satisfies the functional equation where gamma is the gamma function, which is an equality of meromorphic functions valid on the whole complex plane. This equation relates values of the Riemann zeta function at the points S and 1 minus S, owing to the zeros of the sine function. The functional equation implies that zeta has a simple zero at each even negative integer S equals minus 2n. These are known as the trivial zeros of zeta. When S is an even positive integer, the product in gamma on the right is regular and non-zero because gamma has a simple pole. The functional equation thus relates the values of the Riemann zeta function at odd negative integers and even positive integers. The functional equation was established by Riemann in his 1859 paper on the number of primes less than a given magnitude and used to construct the analytic continuation in the first place. An equivalent relationship had been conjectured by Euler over 100 years earlier, in 1749, for the Dirichlet eta function incidentally. This relation is interesting also because it actually exhibits zeta as a Dirichlet series which is convergent in the larger half-plane sigma greater than 0, up to an elementary factor. Riemann also found a symmetric version of the functional equation, given by first defining the functional equation is then given by zeros, the critical line, and the Riemann hypothesis. The functional equation shows that the Riemann zeta function has zeros at -2, -4. These are called the trivial zeros. They are trivial in the sense that their existence is relatively easy to prove, for example, from sin being 0 in the functional equation. The non-trivial zeros have captured far more attention because their distribution not only is far less understood but, more importantly, their study yields impressive results concerning prime numbers and related objects in number theory. It is known that any non-trivial zero lies in the open strip SC, 0 less than re less than 1, which is called the critical strip. The Riemann hypothesis, considered one of the greatest unsolved problems in mathematics, asserts that any non-trivial zero S has re equals 1/2. In the theory of the Riemann zeta function, the set SC, re equals 1/2, is called the critical line. For the Riemann zeta function on the critical line, CZ function, the Hardy-Littlewood conjectures in 1914, Godfrey Harold Hardy proved that has infinitely many zeros. Hardy and John Enzer Littlewood formulated two conjectures on the density and distance between the zeros of on intervals of large positive real numbers. In the following, is the total number of real zeros and the total number of zeros of odd order of the function lying in the interval. For any, there exists a such that when the interval contains a zero of odd order. For any, there exists a and such that the inequality holds when in. These two conjectures opened up new directions in the investigation of the Riemann zeta function. Other results. The location of the Riemann zeta function's zeros is of great importance in the theory of numbers. The prime number theorem is equivalent to the fact that there are no zeros of the zeta function on the re equals 1 line. A better result that follows from an effective form of Vinogradov's mean value theorem is that zeta 0 whenever t3 and the strongest result of this kind one can hope for is the truth of the Riemann hypothesis, which would have many profound consequences in the theory of numbers. It is known that there are infinitely many zeros on the critical line. Littlewood showed that if the sequence contains the imaginary parts of all zeros in the upper half plane in ascending order, then the critical line theorem asserts that a positive percentage of the non-trivial zeros lies on the critical line. In the critical strip, the zero with smallest non-negative imaginary part is 1/2 plus I 14.134725514. The fact that for all complex S1 implies that the zeros of the Riemann zeta function are symmetric about the real axis, combining this symmetry with the functional equation. Furthermore, one sees that the non-trivial zeros are symmetric about the critical line Re equals 1/2. Various properties. For sums involving the zeta function at integer and half-integer values, see rational zeta series. Reciprocal. The reciprocal of the zeta function may be expressed as a Dirichlet series over the Mobius function mu. For every complex number S with real part greater than 1, there are a number of similar relations involving various well-known multiplicative functions. These are given in the article on the Dirichlet series. The Riemann hypothesis is equivalent to the claim that this expression is valid when the real part of S is greater than 1/2. Universality. The critical strip of the Riemann zeta function has the remarkable property of universality. This zeta function universality states that there exists some location on the critical strip that approximates any holomorphic function arbitrarily. Well, since holomorphic functions are very general, this property is quite remarkable. The very first proof of universality was provided by S. M. Thorinin in 1975, which results non-applicable to solve Riemann's hypothesis. A later and more accurate proof was given in 2003 by Garangstis. In 2015, Schwarzenberg gave an even more accurate and general proof of this theorem. Nevertheless, none of the proofs above are definitive or complete, since a definitive proof would imply that Riemann's hypothesis is true. Estimates of the maximum of the modulus of the zeta function. Let the functions and be defined by the equalities here as a sufficiently large positive number. Estimating the values and from below shows how large values can take on short intervals of the critical line or in small neighborhoods of points lying in the critical strip. The case was studied by Ramachandra. The case, whereas a sufficiently large constant is trivial. Karatsuba proved, in particular, that if the values n exceed certain sufficiently small constants, then the estimates hold. Where are certain absolute constants? The argument of the Riemann zeta function. The function is called the argument of the Riemann zeta function. Here is the increment of an arbitrary continuous branch of along the broken line joining the points, and there are some theorems on properties of the function. Among those results are the mean value theorems for and its first integral on intervals of the real line, and also the theorem claiming that every interval for contains at least points where the function changes sign. Earlier similar results were obtained by Atle Selberg for the case. Representations. Dirichlet series. An extension of the area of convergence can be obtained by rearranging the original series. The series converges for, while converges even for. In this way, the area of convergence can be extended to for any Maligne transform. The Maligne transform of a function f is defined as in the region where the integral is defined. There are various expressions for the zeta function as a Maligne transform. If the real part of S is greater than 1, we have where gamma denotes the gamma function. By modifying the contour, Riemann showed that for all S, where the contour C starts and ends at plus infinity and circles the origin once, we can also find expressions which relate to prime numbers and the prime number theorem. If pi is the prime counting function, then for values with Re greater than 1, a similar Maligne transform involves the Riemann prime counting function j, which counts prime powers Pn with a weight of 1, n. So that now we have these expressions can be used to prove the prime number theorem by means of the inverse Maligne transform. Riemann's prime counting function is easier to work with, and pi can be recovered from it by Mobius inversion. Theta functions. The Riemann zeta function can be given formally by a divergent Maligne transform in terms of Jacobi's theta function. However, this integral does not converge for any value of s and so needs to be regularized. This gives the following expression for the zeta function. Laurent series. The Riemann zeta function is meromorphic with a single pole of order 1 at s equals 1. It can therefore be expanded as a Laurent series about s equals 1. The series development then is the constants gamma and here are called the Stieltjes constants, and can be defined by the limit. The constant term gamma 0 is the Euler-Mascheroni constant. Integral for all. The integral relation holds true, which may be used for a numerical evaluation of the zeta function. Rising factorial. Another series development using the rising factorial valid for the entire complex plane is this can be used recursively to extend the Dirichlet series definition to all complex numbers. The Riemann zeta function also appears in a form similar to the Maligne transform in an integral over the Gauss-Kuzmin-Ising operator acting on xs-1. That context gives rise to a series expansion in terms of the falling factorial Hadamard product on the basis of Weierstrass's factorization theorem. Hadamard gave the infinite products expansion where the product is over the non-trivial zeros row of zeta and the letter gamma again denotes the Euler-Mascheroni constant. A simpler infinite products expansion is this form clearly displays the simple pole at s equals 1, the trivial zeros at -2, -4, due to the gamma function term in the denominator, and the non-trivial zeros at s equals rho. Logarithmic derivative on the critical strip, whereas the density of zeros of zeta on the critical strip 0 less than re less than 1. Globally convergent series. A globally convergent series for the zeta function, valid for all complex numbers s except s equals 1 plus 2 pi in log for some integer n, was conjectured by Konrad Knopp and proven by Helmut Hasse in 1930. The series only appeared in an appendix to Hasse's paper, and did not become generally known until it was rediscovered more than 60 years later. Hasse also proved the globally converging series in the same publication. However, recent research indicates that the latter series was discovered earlier, by Joseph Zeta in 1926. Peter Boervine has shown a very rapidly convergent series suitable for high-precision numerical calculations. The algorithm, making use of Chebyshev polynomials, is described in the article on the Dirichlet theta function. Series representation at positive integers via the primorial. Here Pn hash is the primorial sequence and Jk is Jordan's totient function. Applications. The zeta function occurs in applied statistics. Zeta function regularization is used as one possible means of regularization of divergent series and divergent integrals in quantum field theory. In one notable example, the Riemann zeta function shows up explicitly in the calculation of the Casimir effect. The zeta function is also useful for the analysis of dynamical systems. Infinite series. The zeta function evaluated at positive integers appears in infinite series representations of a number of constants. There are more formulas in the article harmonic number. In fact, the even and odd terms give the two sums, and where gamma is Euler's constant, where represents the imaginary part of a complex number. Some zeta series evaluate to more complicated expressions for generalizations. There are a number of related zeta functions that can be considered to be generalizations of the Riemann zeta function. These include the Hurwitz zeta function, which coincides with the Riemann zeta function when q equals 1, the Dirichlet L functions and the Dedekind zeta function. For other related functions see the articles zeta function and L function. The polylogarithm is given by which coincides with the Riemann zeta function when z equals 1. The Lurch transcendent is given by which coincides with the Riemann zeta function when z equals 1 and q equals 1. The Clausen function, CLS, that can be chosen as the real or imaginary part of Lis. The multiple zeta functions are defined by one can analytically continue these functions to the n-dimensional complex space. The special values of these functions are called multiple zeta values by number theorists and have been connected to many different branches in mathematics and physics.